Hello. Hi, my name is Ryan. We're gonna do some Advent of Code stuff because it's December, and I love Elm. So let's take a look at it here. So for those of you who don't know, Advent of Code is like this once a year, every year, like a bunch of random coding problems, and you can choose what language you want to use. I'm gonna use Elm for this because I'm an addict, and I haven't looked at any of the problems or anything. I have no idea what's coming, but I thought I'd make a video series. I'm not going to do all 25. I never do all 25, but I'm going to at least do this one and then try to make more videos like these to kind of walk you through how you can solve made up problems in a language that compiles to JavaScript. So I got my water here. I've got my OBS set up. My face is in a circle. Let's take a sip and let's get started and see what's going on here. Okay, so day one sonar sweep. You're minding your own business on a ship at sea when the overboard alarm goes off. You rush to see if you can help. Apparently, one of the elves tripped and accidentally sent the sleigh keys flying into the ocean. Did not know they had those. Before you know it, you're inside a submarine. The elves keep ready for situations like this. It's covered in Christmas lights, because of course it is, and even has an experimental antenna that should be able to track the keys if you can boost its signal strength high enough. There's a little meter that indicates the antenna signal strength is displaying 0 to 50 stars. Your instincts tell you that in order to save Christmas, you'll need to get all 50 stars by December 25th. Again, it's not going to happen. Collect stars by solving puzzles. 2 puzzles will be made available on each day in the Advent calendar. The second puzzle is unlocked when you complete the first. Each puzzle grants 1 star. Good luck. I think we can do 10. I think we can get 10 stars. 50, we could probably do 10. All right, so let's take a look at this first problem. As the submarine drops below the surface of the ocean, it automatically performs a sonar sweep of the nearby seafloor. On a small screen, the sonar sweep report, your puzzle input, appears. Each line is a measurement of the seafloor depth as the sweep looks further and further away from the submarine. For example, if you had the following report, a bunch of numbers there. This report indicates that scanning outward from the submarine, the sonar sweep found depths of 199, 200, 208, 210, and so on. The first order of business is to figure out how quickly the depth increases, just so you know what you're dealing with. You never know if the keys will get carried into deeper water by an ocean current or a fish or something. To do this, count the number of times the depth measurement increases from the previous measurement. There's no measurement before the first. In the example above, the changes are as follows. So when it went from 199 to 200, it increased, and then 210 to 200 decreased. And the important thing is the first one, you don't say increase or decrease. So in this example, there are 7 measurements that are larger than the previous measurement. How many measurements are larger than the previous measurement? All right, so this is the puzzle input. This is like the example data. Let's just get our environment started up. And by environment started up, I mean, let's set up nothing. Let's go to Ellie app. This is like CodePen for Elm. So if you go to this website, ellieapp.com, you can make your own little Elm app. I'm going to zoom this in so everyone can see it. And I'm just going to clear this out here and get us started with a fresh Elm app. So with Elm, everything we do, we just kind of render as HTML to this screen on the right. So if I want to say hello, I can format my code here. This is what you see here. So it's turning a string into some text that we can throw in onto the right. So for this example puzzle, it's going to be a lot of like string input, and then it might be like a number output or something. So what we're going to do is, instead of using strings all the time, sometimes we're going to want to print like something like, the answer might be number 7. So when I hit compile here, Elm is like a strongly typed language. And all that means is that text definitely needs a string. So the way we can get around that is we can use this quick utility to basically just kind of like format that to a string for us automatically. So what we can do with that is if it's a number, if it's a list of numbers, we can print that to the right, and then we can get our answer, and then whatever answer we get, we're gonna shoot over here in this puzzle. So what I'm gonna do is I'm gonna start with the sample input, And I'm going to see if we can write code that gets us to the answer that they got, which is 7. So if we can get 7, then I'm going to try it with the puzzle input, and then we're going to submit the answer. So that's kind of how it's going to go. So let me just quickly take this input. I'm going to do a multi-line string. In Elm, you use 3 quotes for that. I'm going to paste this here. So we have our input here, and if I wanted, I could just let's say that we had something called answer. So answer 7. So here, this is just going to kind of render it to the screen. So I'm going to put some comments here. So this is going to be main. This is our input, and this is going to be our actual like logic or answer or whatever. So if we wanted, we could say, we could make sure that our string's coming in. Notice there's like new lines and stuff here. We're going to have to like format those out. So what I'm going to do is I am going to basically call the string.lines function. So in Elm, you can call functions like this. But when you start to add more and more features, I'm going to start to show you this thing called a pipeline operator. And that basically allows us to do things step by step, kind of top to bottom. So right now, I've got all my numbers. They're all strings right now. So what I want to do is I want to basically take the result of this, and I'm going to want to turn all of these strings into numbers. So if I try to do that with a list.map, string.fromInt, oops, what this is going to do, or sorry, to int is what we want to do. We want to go from a string to an int. So for the empty strings, we get nothing. For the numbers that succeeded, we're gonna get all these just things. Just is Elm's way of like dealing with like a conditional value. So let's actually take a look at the string docs here. Oops. So this opens up the actual Elm documentation, and so as we code this, we can kind of see how these functions work. So we're using the string.toInt function. So if you give it like 1, 2, 3, it's going to say just 1, 2, 3. It's using this weird maybe type that you might not see from other languages. But basically what maybe does is it either returns a value if the thing worked, or it returns nothing, kind of like null in other languages. But it forces us to handle our code so we don't forget to like handle nulls and accidentally get like a crash. So for example, if we wanted to turn 1, 2, 3 into a number, that would work. But if we try to turn like 3.1, which is like a float, like a decimal number, that would fail. If we put in like a banana or something, like that would also fail. So what we're seeing here is that this, like the new lines and stuff, didn't work. So I could keep writing my code like this, but it's going to kind of get hard to read. So I'm going to show you something called the pipeline syntax in Elm. So what that does is it lets me kind of pass input in one step at a time. So if I compile this, this is what we did before, but instead of saying string.lines input, what we're going to do is we're going to say take input and pipe it into string.lines. So basically hand it as an argument to this function. And we can do the same thing with that list.map that we had before. So instead of using all these parentheses and getting kind of in like this nested parenthesis situation, we can do this. What we also want to do is we don't really care about the like the invalid lines here. So instead of using map, we just filter out the maybes that became nothings. There's a function for that that I know this because I'm familiar with the language. It's also in the docs here, but there's a filter map. And what filter map does is it's just like map, but what it'll do is it'll keep all the maybes that succeeded. So this is actually an example of them using string.toInt, which is perfect because that's what we're using it for. So if you imagine we had a list of all these strings, filter map with string.toInt would only keep the numbers that successfully turned into integers. So instead of having to deal with the nothings and the justs, if we use filter map here, we can actually just get our input. So that was kind of like step 1. So step 1, we took the raw string, which was like, it could be anything. Like I could put like banana here. And what Elm's forcing us to do is like handle like the invalid input. So you see banana got filtered out. So if they ever give us a number that, let's say the puzzle input we have had some type of typo in it, our program wouldn't crash. It would just like kind of dismiss that invalid number. So this is a good spot. So this is the parsed input. Now what we want to do is we want to know between one number and the other, was there an increase or a decrease? So that's going to be a little bit tricky with Elm because we don't have for loops, so we don't have any way to like index into things. What we do have is, let me just give this a name here. I'm just gonna do this here. So I'm gonna capture the parsed input, and the parsed input is what we want. We don't want to deal with a string for this. We want to deal with a list of integers. So this is Elm's way of like basically annotating the type. So answer, this is just gonna print out parsed input for now. So here, this is just a way for us to say like what this is a list of. If we said string, Elm would help us and be like, hey, like you said that this would be a list of strings, but this is actually returning me a list of numbers. So something's up. So these types will help us a little bit later. Input is just a string, in case you're wondering what we might type here. So all these type signatures are optional. They're just going to help us read our code as we add more and more stuff. Okay, so we've got our parsed input. What we need to do is basically compare. We need to compare one number to the number after it. So instead of using a for loop, what we can do is we can basically make a copy of this list with the item shifted over one. So what that looks like is if we grab if we just drop the first item from our list. So here we had 199. If we just drop this is just going to give us 200. So this is like, this is one list. And if we use a map to, we can have like the full list. Sorry, we can have like num1, num2. And then what I'm going to do is I'm just going to show you what they look like. So we can do is have the parsed input here. So what this is doing is this is grouping up those numbers side by side so we can actually do some math on them. So what you're seeing here is that this is comparing the 199 to the 200, and then the next item in the list is doing the 200 to 208. Map2 is kind of like an interesting function, but basically what it's doing is, let's actually take a look at the docs so we can kind of understand it till we get too far ahead of ourselves. So with map2, you can basically like add like two lists together if you want. So for example, if you said 1, 2, 3 and 4, 5, 6, and you ran that through like a map2, you could get like the 1 plus the 4, and that would become 5. Or the 2 plus the 5, and it becomes 7. So basically each item in that list is added together. If we go back to our example, if we didn't do this list.drop, what you'd see is that all the numbers are getting paired with themselves because we put the same two lists in. But by doing the drop one, what we're doing is we're actually pairing the first number of the list with the second number of the list, and like everything's offset by 1 as we go. And that's what's making it so that when we do this, we can see these numbers side by side. And what this takes care of is that weird case in the beginning where there's like nothing to compare. So if you remember the beginning, there was like there's like the no previous measurement. This is only giving us these, which is all we need to compare. So what we can do is we can actually take this. And so I'm going to say this is going to be something called pairs. And a let expression in Elm is basically just a way to make a variable that's kind of only scoped to the answer. So if I said pairs here, we basically still get the same output, but this is like a way for us to kind of keep track of like intermediate values as we're doing our work, so we can give things a name. So we've got our list of pairs. What I want to do with these pairs is I want to run through, and I just want to know, was it an increase, a decrease, or like did nothing change? So I'm going to say to change. And to change is going to be a function. It takes a pair of numbers, and we're going to return like what the, we can call this 2 delta, actually. I'll call this 2 delta. And this is going to return a delta value, which is something we're going to define above here. So what are the options Like, let's talk about like advent of code. So what could happen between two numbers? You could have an increase, you could have a decrease, or if like two numbers are repeated, like there could be no change. So what we want to do is say that the type delta can either be an increase or a decrease. So, and now we get to make our own values instead of having to like use strings for everything. So what this basically does is this will allow us to have like a type of thing that we can like look at. So I'm gonna call this the first number and the second number. So I can say if the second number minus the first number is greater than 0, then that was an increase. Else, I'm going to kind of copy this same thing here, and I'm going to say if it was less than 0, then it was a decrease, and then this is saying there was no change. So I'm going to format that. And so what we can do here is we can see for each one of these, increase, 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 decrease, increase, increase. So we have 3 increases, 1 decrease, 3 increases, 1 decrease. And I think that's what we saw in the code. 3, 1, 3, 1, and then 1. So it looks like we're okay. Now all we need to do is we just need to count up all the ones that were increase. So what we can do is we can say list.filter, and then this is a delta. Let's actually just make this a function, is increase. So is increase is going to take in each delta one at a time and just tell us true or false. Is that delta an increase or not? So this will be an easy function, right? So if the delta is increase, we return true. So now instead of increase, 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 we're basically using the filter function. So if we use map, we could get like true, 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 false. But with filter, what we're doing is saying only keep the ones that were increases. So we did that, and then as one last step, all we have to do is get the length of the list. And that's 7. So that's the number that we're looking for. So I think our logic's okay. Let's test it on the real puzzle input and see if what we're writing is legit. So this is my puzzle input. If you do this on your own, you're going to get a different string here. So all you have to do, by the way, for advent of code, you can just click like a login button at the top, sign in with GitHub, and then you're all set. So if you want to like take this code, follow along, please, yeah, feel free to do so. All this stuff is totally free, and you don't even need to install anything. You can just kind of do this all in your browser. So this is our test input. I'm just going to call this test input. Oops. And then we're just gonna. I just wanted to keep that around. And then I'm going to basically do the same thing here. So these are all our numbers here, that's a lot of numbers. I'm trying to crash my browser. So if I run this, all these numbers, it's a 1624. And let's see if that's right. Hooray! That's the right answer. So we got our 1 gold star, and we're a little bit closer. So I've officially done at least one advent of code problem, which is really all I could have asked for this holiday season. It's beautiful. So usually with these problems, they give you a part 2, which kind of like adds on to the problem to see if like your code can like handle doing something slightly different, or if you like really hard coded it to the problem. All right, here we go. This is freaky. So considering every single measurement isn't as useful as you expected, there's just too much noise in the data. Instead, consider sums of a 3 measurement sliding window. I'm gonna have to take a drink of water for this one. This is getting wild. Again, considering the above example, so 199 A, AB, ABC, BCD, E. This is really weird. So it says start by comparing the first and second 3 measurement windows. The measurements in the first window are marked A. So 199, 200, 208. Their sum is 607. The second window is marked B. Okay. Its sum is 618. Sum of measurements in the second window is larger than the sum of the first. So this is weird. This is weird. The first comparison increased. Okay, so A compared to B, there was an increase. Okay, I see. Your goal now is to count the number of times the sum of measurements in the sliding window increased from the previous sum. So compare A with B, then compare B with C, C with D, and so on. Stop when there aren't enough measurements left to create a 3-measurement sum. In the above example, the sum of each 3-measurement window is as follows. Okay. Got it. So this is them adding all this up, 199, 200, 208. And basically they're adding it all up. They're kind of like indexing it based on the letter. So they're like grouping all these numbers up by this letter. And then they're going from top to bottom with the letter to see like, to see like what goes first. Okay, so they say 5 has increased. Okay, so what we're gonna do is I'm gonna save, oops, this is gonna be admin of code 1.1, and I'm gonna click the save button here. I'm actually gonna undo this just so that if you decide to use this link, I'll post this link in the YouTube video below. You can click on it and like play around with the code if you want. But I'm going to save it without my personal input because it was just so long, it was kind of hard to read it. But if you run this, you should get the 7 that you expect. So I'm going to just put this in my notes here and bring this over here and just kind of paste that. Cool. Okie dokie. So that is part 1.1. What I'm going to do is I'm going to copy this and I'm going to make a new LE. So we're going to go over here and just do leapp.com. Let's give me a fresh one, and I'm just going to paste what we had before, run it, and it should just work. Cool. This is all just like HTML styling stuff, so I usually just collapse this. So when you load up LE, you probably don't need to mess with that stuff. Okay, cool. So our code right now, our input doesn't look like this. What we need is we need the new input. I'm going to close this out. So the new input looks something like this. And what's interesting about this is we're going to be going row by row, and we can't just use our parsed input like this anymore because our parsed input is going to fail for everything. If we look at the pairs that we get back, oops, I'm going to just kind of delete this. Oops. So I'm going to, I wish I could comment things out with multiple lines. So in Elm, to do a multi-line comment, you can do basically this. So let's take a look at our parsed input real quick. This isn't what we want. And the reason this isn't what we want is because none of these numbers are succeeding. We're basically trying to turn this whole line into a number, and that's not going to work. None of these are going to work. So parsed input isn't going to be a list of integers anymore. So let's just kind of start. Let's start from the raw data and try to see like what we can create. So what I'm thinking is each of these numbers, I kind of want to like associate with A or associate it with B or associate it with C. So normally when you want to have like a key that like looks up a value, you want to use something like a dictionary. Other languages might call it a map. But in Elm, we have this module called dict. And so if we import that, this is available in the core library. So basically what that allows us to do is it allows us to like quickly look things up by like name. Important thing to know is that the order can get jumbled with a dictionary. So the order isn't guaranteed, so that might bite us later. I don't think it will for this puzzle. We'll have to see what the puzzle input is. But let's just assume it won't, and then we'll see if the input is all jumbled up. And if it is, then we might have to keep track of like what order we saw keys in. Again, I don't think that's an issue. So what we need to do is we need to look at each of these lines. And so we did a good job here of like breaking these apart into like these separate strings. But what we need to do is like split them on spaces. So let's just quickly do that. List dot map string dot split. Does that work? String dot split. Oh, it expects a string, not a character. I use single quotes. Okay, so what I think we want to do is we want to simplify this list. So what I'm going to do is I'm going to basically for each item in this list, I am going to filter out the empty strings. So is non-empty string. So we're going to make this function together. So is non-empty string is going to take a string and return a Boolean if it's not empty. And so we can just use some built-in Elm helpers to do this. So string.isEmpty. I think string.empty is the function. Let's take a look at the docs. So string is empty. Okay, that is right. So this tells us if it is empty, what we're going to do is we're going to run that. And then we're going to say, we can say like not. So what this is going to do is non-empty string. The stop map, string filter map is non-empty string. Oh, this isn't a list of lists. This is a list of strings. Okay. It's a list of strings. What is this thing? Let's take a look at what we had. So here we have a list of lists. And then I'm gonna just see what this is. Oh, we want to filter. Sometimes these can get a little confusing. Okay, so this is basically just keeping around the stuff without all the spaces in it. So here we have like our 199, and then we have our like A, B, C, all that stuff. So what we can do with these like little lists is we can start looping through this and grouping things based on their letter. So I'm just gonna make a function that says group by letter. And so as you can see, the group by letter input is going to be this list of lists of strings, which is it's a little nested and a little bit weird, but we're going to make some sense out of it. And what we want at the end is we're going to actually want a dictionary that maps like letters to integers. So I'm going to start with a list of integers. So we're going to say like, for example, we can map like A to a list of 199, 200, and 208, and then from there we can sum them up after that. But I think it would be less confusing. List of strings. I'm gonna call it as crazy as it is, as opposed to trying to give it like a cute name that makes it look less scary. Okay, so what's a letter? Sometimes in Elm you can make this thing called the type alias, and a type alias just helps you like read stuff. So a letter is really just a string under the hood, but when it comes to like understanding what this dictionary is mapping things to, I think it's useful to like call the key a letter itself. So with the dictionary, this is the key, and this is like the value that it's storing. So to get started, what we can do is we can do a list.foldL. And so a fold L is basically, it's going to take each item, so like each list of strings from this list of strings, and it's going to take in the current dictionary. So I'm just going to call that dictionary, and it's going to return the new dictionary. So how list.foldL works is we're going to give it the initial state. So initially we're going to start with an empty dictionary, and then we're going to give it the input, so like the list of things. So we're going to do this. I'm going to break this out. This is called a lambda in Elm. It's just like an inline function. I'm going to try to avoid those as much as possible because I think it's easier to read if you give functions names. And this is going to be like add to letter dict. And what that's going to do is that's going to be this function, but we're going to give it a type signature so that Elm can help us if we do anything wrong. So to be clear what this is, it's going to start with a list of strings. Because remember the fold L and the maps, all these functions, what they're doing is they're dealing with one item at a time, so you don't have to deal with like the crazy big list and like for loop through it or something like that. And it's going to take in basically the current dictionary, and what it wants you to do is return like the new, like the modified dictionary. So what I'm going to do here is I'm just going to not change the dictionary at all. So I'm gonna ignore the list that I get in, and I think what we're gonna see at the end of this, if we don't have a compiler problem, is we're just gonna see an empty dictionary. It should say like dict.fromList with like an empty string. Okay, cool. So this is an empty list. So what we want to do, let's keep in mind what like list of strings was, right? So before we did this, I'm going to use this to comment this line out. Before we did this, we're kind of looking at things here. So I think what we want to do is we want to kind of parse this. So we're going to use a case expression on this list of strings. And we're going to think of the different cases. So if it's an empty list, we're not going to make any changes. So for example, if we saw this, there's nothing to assign. There's no letters, there's no numbers. We're not going to mess with that. So we're going to leave the list alone. If we had basically just like a number and then there was no letters, there's also nothing we can do to the dictionary. We can't update it in any way. But if we have a number and then like letters, this would be like a list of all the letters that we get. We want to do something with the dictionary. So we want to like loop through the letters and we want to update the dictionary. So what we're going to do is we're going to do another list.foldl here. And this is going to take each letter one at a time. So like for the first one, it's just going to be A. For the second one, it's going to A and B. This one's going to be A, B, and C. So what this is going to do is, depending on which one we get, we might get, so let's just focus on one thing at a time. So if this comes in, our number is going to be 199, and our letter is going to be A. Our letters is going to be a list where it's just A. So what we want to do is we're going to want to basically insert, we're going to actually update our dictionary and then say like what we want to do. So if the dictionary is empty, what we're going to try to do is we're going to try to update at that letter. And let's take a look at the dict.update function. Take a look at what this looks like. So what it's going to do is it's going to take our letter. That's our comparable. That's like the key that we're storing. And it's going to take a function going from maybe a list of integers to a maybe list of integers. So this is going to be to maybe list int. We're going to pass this number in here. And then we're going to do that. Yeah. So I'm going to call this the current dictionary so we don't confuse it with this one we got passed in here. And what we're going to do is we're going to call that on the current dictionary. And here we are going to start the initial thing that we're going to loop through is this dictionary. We're going to loop through all the letters. Okay, so if I tried to compile this right now, it would yell at me and it would say, what's this? I don't know what this function is. So what we're going to do is we're just going to quickly define this. This was our maybe values. And so for the values of our dictionary are just a list of numbers to a maybe value. So a good question is what's up with all the maybes here? So if I gave you a dictionary and I said, get me all the numbers at A, we're going to be in one of two states. So, so it's going to be a maybe list. So maybe no one has ever inserted a value at A. So like this is the first time we're seeing it, in which case, if there's like nothing in there, we're just going to like initialize the list and we're going to give it the number that we saw. So we're going to pretend this is decoded. Right now this is going to fail because number is still a string. I'll say case string.toInt num string of just num. So if we could turn that number, basically if we could turn 199 into an integer, we do it. If for some reason it was like some invalid integer string like banana, it's going to ignore it here and it's just going to return the dict as is. But basically what this is going to do is it's going to say, hey, like if this is the first time I'm seeing the letter A, I'm just going to like insert that number and I'm going to return that as a maybe list. So that's one thing. But if there's an existing list, what I'm going to do is I'm going to just append number to the existing list. So you might be seeing these colons here. This is Elm's way of saying like append to the front of a list. It's like a little operator shortcut. So that was a lot to take in, but basically when we call group by letter now, hopefully what we're going to see is that all the A's are grouped together, all the B's are grouped together, all the C's are grouped together. And that's what we do see. So we're seeing A, it has 208, 200, and 199. Remember how we're appending from the front? That's why we're seeing these things backwards. So that was kind of a lot to digest. We're definitely going to break that down before we submit our answer. Let's just make sure that this is correct, and then we'll explain the solution a little bit more. Because this is kind of like a little bit intimidating if you're new to the language and new to the syntax. Okay, so right now where we're at is we have a dictionary, and it's mapping letters to a list of numbers. So what we can do is we can turn this back into a list. So instead of dict.fromList, this will just be dict.toList. And then we can map through each item. So keep in mind each item is a pair. So we can say sum pair. And I love how I'm doing all this in parsed input. Kind of crazy. This is really getting closer to answer than parsed input. So I'm gonna get rid of this. So what we're gonna do is we are going to make a sum pair function. A pair is going to take in a pair, which is going to be a letter and a list of numbers. And it's going to return basically a letter and a sum. So this is going to be letter, this could be numbers. And then what we're going to do is we're actually going to just turn the letter as is. We're not going to change that part, but then we're going to use list.sum, which is a built-in method that just adds up a bunch of numbers in a list. Excuse me. So we do have A607, B618, C618. And so what we're seeing here is this increased, hey look, no change. I knew it was real. Decreased, increased, increased. So what we're going to be able to do now is we're going to be able to compare and use that same code that I think I just accidentally deleted. Let me undo that because I want to copy that on my clipboard before. There we go. So we're back to where we were, right? Okay. And what we want to do is now we're going to basically just take the second item in this pair. So I'm going to say list.map and then tuple.second. Tuples are these pairs that we've been dealing with the whole time. Now I have that. And then what I want to do is before I was basically dealing with these sums, what I want to do is I want to convert these to a delta, see if it increased, and then get the length. So this is the code we're going to be able to reuse, which is really nice. So if I format that, to delta, to delta needs, that's right, we're going to have to do the pair thing completely. Okay, so I guess all this work was for that parsed input, right? Because all this work was just to get the list of numbers that we had in the first half of the problem. So I'm going to call this parsed input again. I was totally wrong to get rid of that. And then answer is going to be what we had before. So answer is going to take that parsed input and it's going to return our number. And it looks like answer is actually the exact code that we used before. Because now that we have a list of numbers, it looks like the first half of the problem that we solved, where we just had things that looked like this. So all that work was really just turning this into the same input we have here, so we could completely reuse the answer we had before. That was close, I almost did more work. But here you see there are 5 sums that are larger than the previous sum. So this might work. The reason this won't work is if the letters aren't in alphabetical order. Dictionary inserts kind of sort themselves to like be efficient. So I'm afraid that we're gonna have to keep track of the length, but we'll take a look and we'll see. So let's take a look at the puzzle input. Oh, no way. Oh, I should have looked at the puzzle input. Is this? Oh, the puzzle input hasn't changed. I thought I had to parse these letters. Oh no, what a waste of time. Okay. Basically what we want to do is we want to group things in batches of 3. I totally misunderstood. Oh man. Okay. So I've got good news and bad news. The good news is I'm deleting a lot of this code. The bad news is I didn't understand what the assignment was. So I feel pretty stupid. So really what we're dealing with isn't all these H's and all that. We're just dealing with this. I should have checked the puzzle input before I did all this work. We're not going to be grouping by letter. What we're going to do is be grouping by like index. So our list.map3 is, let's just go back. So I'm going to save what we have here. This was cool. This does work. I'm going to save this. And I'll give you guys a link to this. This is a lot more complicated than we needed it to be. So I might edit out the video. Nah, I'd like to show you my failure. I think it's funnier that way. So I'm going to keep this in our notes. But what I'm going to do is actually open up our previous version. So what was happening before with 7 was let's take a look at our pairs function. So I'm just going to comment this out. So back when we were here, oops. Back when we were here, what we were doing is we were comparing this number to this number. But what we need to do now is we need to compare the sum of these 3 to the sum of these 3. So that's going to be a little bit easier. So what we need to do is basically group things by 3 and then sum those up. So instead of using a list.map2, see how we kind of grouped these 2 together? What we can actually do is we can use a list.map3. And so this is actually pushing the boundaries of tuples. They only support up to 3, so we lucked out. But if we do this one more time, oops, this is a list of int. We're going to have these triples, and they're going to be grouped together. So if we took the same code we had for part 1 before, and we basically use this triple function, what we can do is we can sum these up, and then the sum of those things will become the input to the next function. So let me just copy this. This isn't really pairs, this is triples. So what I'm going to do is I'm going to copy this. I'm going to undo what I did here. We're going to go back to our map2. So what we want is we're going to have a 2 triple. We're going to have the triples here. Format wants me to do this. Okay. So really these are all okay, but the answer isn't going to be operating directly on the input. So I'm going to say these are going to be our numbers. So if I ran our previous code on like a variable, so if I basically made answer a function where answer takes in a list of numbers and gives us like the sums, I could, like our previous thing was just using parsed input for this. It's just like an argument, and it gave us 7. But what we want to do is we actually just want to, instead of calling answer on parsed input, we're going to use these triples, and then we're going to sum the triples. And that's going to give us our list of ints. And what that looks like is we're going to do list.map, and we're going to have A, B, and C, like basically our first, our second, and our third numbers. And we're just going to return A plus B plus C. And that's going to be for the triples that we had. So in order to get from one to the other, all we're going to do is type in triples. Oops. This is going to be the sum triples. Think. Oh, you know what? Sorry, I forgot to put that in both places. So this should be 5. Okay, cool. All right, so that feels better. We got to reuse our entire function from part one. We just had to parameterize this list of integers. And then what we did at the end was we, instead of always giving in like the direct input, we basically kind of changed the input to make it the same shape so we could reuse our function. So triples is a list of integers. Let me break this apart so you can see kind of what we did. So answer, I'm going to use the pipelines because I think they really help when you're trying to like read what's going on here. All the parentheses can get in the way. This is the same thing. So before we were calling our code on the parsed input directly, and that's what gave us the 7. Here we're calling it on like our transformed input. So if I wanted to show you what that input looked like, it was kind of grouping things like that. And then we summed them together, and that was sum of triples. And then the final step was to run that through our answer function, which gives us 5. So I'm going to take our input. I forgot that admin of code does that, where the input's the same sometimes. I'm going to run it, and it's going to say 0. Dang it. I pasted in the old problem. That's why it didn't work. Okay, 1653. Is that right? Yeah, I think I was changing the this is our bad Ellie. This is the one that had the crazy code in it. Sorry. Okay, but this is it. 1653. I think that's what we had for the last one. Did I not change this to say answer some triples? 1653 is what it says. All right, let's paste it in and see if we're right. Oh, wow. That's it. Okay. So that's 2 stars. We did it. That is day 1. If we return to the advent calendar, gosh dang it. Okay, I waited so late in the day to do this problem that now part 2 is available. So I will try to hop on tomorrow and then give you an answer to part 2. We can pretty much ignore what I did for the dictionary stuff. If you are curious about what all that was, there is an Elm guide here. But we don't need to dive into it right now. But I did some interesting stuff with basically with dictionaries. So there's a really cool interactive guide. If you want to like play around with it, you can like kind of do this here and like learn as you go. But it turns out all that work I did. So I'm gonna rename this to part 2. I'm gonna save that. And then these are going to be my solutions, and I'm going to let you have these. Feel free to do it with your own. Oops. Sheet 5 again. Okay. Save that one more time so you don't have my crazy big input. But that is how I did it with Elm. Let's take a look. The code isn't too bad. I think it's pretty doable. So I think the weirdest parts of the puzzle that we had to deal with, like the weirdest parts of the language, I would have to say the pipeline's a little bit strange. So if you're curious about how pipelines work, you can see functions. It's the easiest way to show. So yeah, core language. Oops. So you can see this is how we call functions. I don't know if does the guide introduce people to pipeline operators? Maybe not. Maybe it's not really relevant. It's just kind of a preference I have. So you might see this in Elm code, the pipelines, and that's basically just piping things in. The other thing that was a little bit weird is map 3. It's kind of like a mind-bending principle, and it really does help to have like smaller examples. So when it comes to like wrapping your head around that, I think one, if you just take this code and you kind of play around with it yourself, that's one way to do it. But the other thing is that the guide has really nice examples for like kind of seeing what's going on. So with our map 3, we kind of did like almost a tuple pair for our triples, but instead of pairing it, we tripled it. So what we're doing here is basically shifting things over by 1, shifting the whole list over by 2, and then just grouping things in that first row. So yeah, so if you're curious about that, definitely check out. I'll have a link to this. This is the Elm core library. So there's like all these things here. You can search for lists, search for strings. I'll put that in the video. I'll also put, this is the Elm guide. And so if you're new to the language, definitely check out this guide. This is how I got started and kind of like wrap my brain around the syntax. And of course, if you're new to Elm, there is an Elmlang Slack. And there's a beginners channel in there that's really, really nice. So if you put your email in there, you can come say hey. You can at me directly. My name's just Ryan, just at Ryan. I was the first one to get in there, so I got the cool username. So if you enjoyed watching the video, feel free to like it if you want, but definitely swing by the Slack and come just yell at me and say it was great. I'd really appreciate that. And feel free to share it with whoever you want. And yeah, it's been a blast. Thanks so much. Happy admin of code. See you tomorrow, maybe? Yeah, see you tomorrow.